Happy morning to all. Anyhow, we finished that D block elements. That means P block elements over, D block element over, and the last one, the periodic classification value, F block element is called as an inner transition element. Okay, inner transition element. Here the inner transition element having only two series. One is a Lanthanide series and another one is an Actinide series. The Lanthanide series having 14 elements and also having the Actinide series as having 14 elements. Lanthanide series, the 14 element, the first element is starting with cerium and ends with lutetium. And about that Actinide series, there is a next. It is start with first element is thorium and he ends with lawrencium. Okay, anyhow 14 elements. Here in today our learning objective is to learn about that the electronic configuration of how to write the electronic configuration of lanthanides and actinides. Okay, lanthanides and actinides, and one of the important board exam question, repeating question. Write the differences between lanthanides and actinides. Write the differences between lanthanides and actinides. This is one of the important question. Okay. Repeating board exam question. So all of you should learn the important question. Okay. Today our learning objectives to learn about the electronic configuration of lanthanides and actinides. And today we should learn which the question means. Write the differences between lanthanides and actinides. Anyhow, about the position in the periodic table where this inner transition elements are occupied. Okay. Before that, few points we can learn about that. Here the positions are justified as to one. Number one, lanthanides have the general electronic configuration. Okay. Here general electronic configuration. What is the electronic configuration? I will write the board. Okay. Let's have one general electronic configuration. And the common oxidation state of lanthanides is +3. What is the common oxidation state of lanthanides is +3. All of these elements having similar physical and chemical properties. These elements are having similar physical and chemical properties. Anyhow, first we should write the electronic configuration of this inner transition element. Please all of you take the book. We should write the electronic configuration. Previous I told you about that, how to write the electronic configuration while I am taking the lesson P block, D block, etc. Am I right? So again, shall we continue how to write the electronic configuration? First we start with 1s, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6p, 6f, 7s, etc. Okay. Anyhow, first one, second one, third one, fourth one, fifth one, sixth one, seventh one. Okay, am I right? Then all the S subshell we can be accommodated. S subshell, all the S subshell we can be accommodated. Maximum 2 electron. P subshell we can be accommodated 6 electron the maximum. And D subshell we can be accommodated 10 electron the maximum. And F subshell we can be accommodate 14 electrons the maximum. Okay, anyhow, here it tells about the electronic configuration of lanthanides. Am I right? Electronic configuration here about the actual electronic configuration of the expected electronic configuration. What is the expected electronic configuration of lanthanides is Xe 4F1 5 is 0 6x2. Okay, Anyhow, the expected electronic configuration of lanthanides is Xe xenon, 4f1, 5d0, 6x2. Okay, but the actual electronic configuration is Xe xenon, 4f0, 5d1, 6x2. Okay, here what is the expected electronic configuration and what is about the actual electronic configuration? That you should be learned. The expected electronic configuration is Xe 4s1, 5d0, 6s2. But here the actual electronic configuration is Xe 4f0, 5d1, 6x2. Okay. Anyhow, we shall write the electronic configuration from the atomic number 57. Okay. Atomic number 57 is start with the lanthanum and ends with the lutetium 71. The start with the atomic number 57 to about the 71. 57 started with, that is a lanthanum La and start with the cerium etc. up to lutetium, ytterbium means 70 and about the lutetium is about the 71, the atomic number. And we can start with 1. And before writing, we should be remember that one. In lanthanide series, we should not write 4f2 and 4f8. It is not possible. In the F block series. F block means lanthanum series. Okay, the lanthanum series 4f2 and 4f8 is not possible. Starting with the 4f0 and ends with the 4f40, that is okay. But there is no 4f1 having, that is cerium, 4f2 not having. Okay, 4f2 not having. Then 4f3, 4f4, 4f5, 4f6, 4f7. Again starting with the 4f7, 4f8 not having, 4f9, 4f10, 4f11, 4f12, 4f13 and 14. Okay, there is no 4f2 and 4f8. Okay, don't forget that. Okay, and we can start with the lanthanum. Lanthanum is about 57. Okay, here we are using, for writing the short form, we are using xenon. Xenon. It is I told you that it is one of the noble gas, inert gas, rare gas. We are using the noble gas. Xenon goes to 54. Okay, that ends to, all of you know that one. That's 18, group number 18. Okay, group number 18 is completely filled and it is started with and ends with 5p6. 5p6, 4d10, 5p6 here, 4d10, 5p6, it ends with 4d10, 5p6. That means up to this much. Okay, shall I once again write it and we can count the number 1s2, EC is equal to 1s2, second one line is 4, second one, 2s2, next one, 2p6, next one, 3s2, next one, 3p6, next one, 4s2, next one, 3d10, next one, 4p6, 5s2, after that 4d10, 5p6, 6s2. Okay, let us count these numbers: 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, next one 54. This much is for xenon. Okay, xenon goes to 54. Xenon is 54 here. Okay, 54. Remaining we can be right. Remaining for lanthanum is atomic number is 57. 57 minus 54 we get remain only 3. Am I right? Remaining we have only 3. So we are writing Xe, that is xenon 54 over next orbital after the here 5p. Don't write the 6s. You should be started here 4f, next to 5d, last only 6s. Okay, here am I right? Here start with xenon, ends with xenon. After finishing xenon, not write 6s, but to start with 4f, 5d, next 6s. Okay, then you write 4f 0. Okay, there is no electron on the f subshell. 4f 0. Next about 5d 1. Next 6s2. This is the electronic configuration of lanthanum. Here, electronic configuration of lanthanum. Next about the cerium. For atomic number is 57. Okay, 57. Next about atomic number 58 goes to cerium. That is symbol is Ce. How to write cerium? That is 54 over for xenon Xe. Okay, over. Next you start with 4f1. 4f1. Okay, 4f1. 4f1. 5d1 and 6s2. Okay, that is 54, 55, 56 plus 2, 58. This is atomic number of cerium is 58. The electronic configuration of cerium is what? Xe, 4f1, 5d1, 6s2. Okay, I told you that there is don't write about the 4f2. Okay, I told you that. You did not write that about the 4f2 because 4f2 is not configuration for lanthanides. Next you write the 4f3. Okay, that is PR. Atomic number is PR is about 58. Sorry, 59. 59. How will you write the electronic configuration? Okay, how will you write the electronic configuration? There is no 4f2. You should be right 4f3. Start with 4f3. Xenon 4f3. Okay, 4f3. Next 5d0. 5d0. 6s2. Okay, because atomic number is how much? 59. 54 over. Remaining only 4 only having. Am I right? 56. 56 is over. Remaining how much having? Sorry, 54. 54 over. Next about 4 of 3. 4 of 3. Next 6s2. Clear? Next about neodymium. That is the symbol is Nd. Nd. Okay. The Nd, the atomic number of Nd is 70. I think that 70. Sorry, 70 not 60. Atomic number 60. Already 54 is over up to how much? 5p6. 5p6. That is xenon. Xenon. 54 is over. Remaining how much? Remaining about 4 of 4. Starting with 4 of 4. 5d0. 5d0. Next about 6s2. Okay. That is about 54 over 54 plus 6, 60. 54 plus 6, 60. Xenon is 54. 54 plus 6, 60. Okay, clear. Next about we are writing PM. What is about the PM? Promethium. Promethium. Okay. Promethium, the atomic number is 61. Promethium, the atomic number is 61. We start with 4 of 5. 4 of 5. 5d0. 6s2. Okay. Xenon Xe 4f5 5d0 6s2. Like that you should be right all the electronic configuration. And one of the important one is about the EU and the GD. Okay, EU. EU, okay, EU. The atomic number of EU is equal to 63. Europium, we are saying about that europium, about it is half filled in the F subshell. Half filled, okay, that is, you should be right. Xenon, that is about the 54, am I right? 4F7, it is 4F14 is completely filled. 4F14 is completely filled. Half filled means 4F7 and 5D is 0 and 5D is 0 and 6 is 2. This is about the europium, okay. Okay, Europe, EU. Next about the GD. This is also important. GD is 64. This is also half filled, okay. This is also half filled. And one more electron goes to 5D. One more electron goes to 5D. That is how to write? Xenon, that is a atomic number finished 54. 4F7, 5D1, 6H2. That means 54 plus 7, that is, I think that's 71, 72 plus 2, 74. Sorry, 54 plus 6, 60, 61, 62 plus 2, 64. Here. These are the electronic configuration. And the last one, don't forget that the last two, that is atomic number 70 and 71. Atomic number 70 and 71 are completely filled in F subshell. Completely filled. Okay? That is YB, ytterbium. YB is atomic number is 70. And about the lutetium, that is LU is atomic number 71. Okay. About how to write the electronic configuration, that is XE, xenon goes to 54, and about 4F40 is completely filled. In 4F40 it is completely filled, and about that 5D have no electron, and about the 7s2. Okay, 5D after that, sorry, not 7s2. About that 6s2, okay, 6s2. This is about the ytterbium configuration. What about the lutetium configuration? Lutetium, the atomic number is 70, 71. One more electron goes to 5D. One electron goes to 5D. So 4F also completely filled and 6s also completely filled. That is Xe LU is equal to 71, Xe 4F14, 5D1, 6s2. Here about that we can get the correct answer. Okay, anyhow, try to write all the electronic configuration. Okay, about the atomic number GD, I told you about the atomic number GD and LU, that is 64 and 71 are half filled. Okay, 64 is a half filled and 71 is a completely filled in the F subshell. Yeah? And also one electron enters in 5D orbitals. Okay? About the GD, that is atomic number 64 and the lutetium 71. Lutetium, that is GD have half filled in their F subshell, and about the lutetium having completely filled in the F subshell. Only one electron enters in the 5D orbital. This is the electronic configuration. And about similarly, we can write the configuration. What is the general electronic configuration of F block element? That is Lanthanide series. Only for the Lanthanide series, 4F series can be written as the general electronic configuration. Xe 4F 1 to 14. Xe 4F 1 to 14. 5D 0 to 1. Okay, 0 to 1. Start with 0. 0 to 1 and 6s2. This is the general electronic configuration of about the lanthanides or lanthanum series. Okay, lanthanides or lanthanum series. Okay, anyhow, this is the general for the one-word question. This is the general electronic configuration of lanthanides, that is Xe 4F 1 to 14, 1 to 14, 5D 0 to 1, 6s2. Okay. Next about the oxidation state of lanthanides. Okay, about the oxidation state. Here, it has the common oxidation state and also having the variable oxidation state. When we when we goes to left to right from lanthanum to lutetium, from lanthanum, that is LA to LU, lanthanum to lutetium, that is atomic number 57 to 51. Here the oxidation state can be also variable oxidation state. Here the common oxidation state, this is very, very important for the one word. The common oxidation state +3. The common oxidation state is +3. And about the uncommon oxidation state, we can say that other more also. Lanthanides also show either +2 and +4 uncommon, +2 and +4 oxidation state. It is a common oxidation state and also some variable oxidation state, that is, and also either +2 and +4 the oxidation state. Okay. Next about the atomic and ionic radii. Atomic and ionic radii of lanthanides. Here as per our textbook having one graph having, okay, that is about that one of the graph like that. Okay, from the atomic the elements are filled like that from lanthanum to, okay, lanthanum to lutetium, and about the atomic radii of variation of atomic radii of lanthanides. Okay. About here the size is like that, decreasing, okay, like that, decreasing. As we move across the 4F series, the atomic and the ionic radii of lanthanides series is gradually decrease when the atomic number is increased. Clear? Okay. Here about that, the atomic and ionic radii of lanthanides show a gradual decrease with increase in atomic number. Whenever the atomic number is increased, the atomic size is also decrease. Okay. About that, this is the size decrease in ionic radii is called lanthanide contraction. The size is decreases due to the decrease in size. It causes the lanthanide contraction. Contraction means contraction, size is reduced, that is called what? Lanthanide contraction. It is happened in lanthanides, so we are telling about the lanthanide contraction. Suppose it is happened in actinides, we are saying that actinide contraction. Okay? Why it is happened? When the atomic number is increasing, the size is gradually decreasing. Atomic number is increasing, size is gradually decreasing. Here, the decrease in ionic size, the size is decreasing. So we are seeing what? Lanthanide contraction. Okay, let us you can see the graph in the textbook. Okay, then what is the causes of lanthanide contraction? What are the causes? Causes of lanthanide contraction. Here, as we move from one element to other element, that means lanthanum, cerium, praseodymium, neodymium, etc., promethium, like we are going like that is atomic number 57, 58, 59, 60, 61, like that. Okay. From one element to other element, for the 4F series, the nuclear charge is increases. What happens? When the atomic number is increases, the nuclear charge is increases. Atomic number is increases. That means one element to other element. The atomic number is increases. The nuclear charges also increases by 1 unit, and also an additional electron is added to the same inner 4F subshell. Okay. Then the 4F subshell have a diffused shape. Which shape? Diffused shape. Therefore, the shielding effect of 4F electrons are relatively poor. Okay. Hence, the increase the nuclear charge, the valence shell is pulled slightly towards the nucleus. So the effective nuclear charge experienced by the flow of electron and increase the size of Ln3 plus ions and decreases. Size decreases. Flow of electron increases and the size of Ln3 plus ions is decreases. Here about what are the consequences? What are the consequences of Landoride contraction? What are the consequences? What are the consequences of Landoride contraction? Here, in the fourth series, atomic radius decreases. Okay, atomic radius, that is the fourth series, only 10 pm decreases in atomic radii and 20 pm decreases in ionic radii is observed. Here, what is that? About the in the complete fourth series, only 10 pm parts per million. Okay. 10 pm that decrease in atomic radii. Atomic radii decreases, and about that decrease in ionic radii also. Here atomic radii also decreasing. How much? Atomic radius means only 10 pm decrease in atomic radii and 20 pm decrease in ionic radii. This is why this happened means there is a very small change in the radii of lanthanides and their chemical properties are quite similar. All the elements, the chemical properties are nearest almost similar. So there is a very small change in the atomic radii. Okay. So it is also happened the consequence in the Landoride contraction. Next about that we can discuss the same. We can discuss about the actinide. About the actinide. What is the general electronic configuration that we discuss about that electronic configuration? First, there are 14 elements in the actinide series. How much element? 14 elements. That means we start with thorium to lawrencium. Okay, thorium to lawrencium. The thorium atomic number is 90. Thorium atomic number is 90, and about the lawrencium atomic number is 103. Okay, the thorium atomic number is 90, and about the lawrencium atomic number is 103. And the actinium series, that is about the 89 actinium. Okay, AC. We are saying AC. Here and about here. These are all radioactive elements. Okay, mostly all the actinides are radioactive. These are what? Radioactive elements, and also most of them are short half-lives. Okay, and about only thorium and uranium are the significant amount of nature. Significant in nature, only a small amount. And about a trace amount of polonium are found in uranium ores. Anyhow, we should be write the electronic configuration of actinide series. How do you write the electronic configuration? Here we are using the noble gas is radon. Okay, radon we are using. What is the atomic number of radon? Radon means atomic number is, I think, that 86. Rn is equal to 86. Okay, atomic number is 86. What about the lanthanides? Which noble gas we are using? Xenon. What's the atomic number? 54. There we are using xenon 54. Here we are using radon. That is the atomic number is 86. Here also we should not write about the phi f1, phi f1, phi f5 and phi f8. Okay. This configuration we cannot take this configuration. Which are the configurations we cannot take? Phi f1, phi f5 and phi f8. Okay. Here we shall write the configuration. That is 1s2, 1s, 2s, 2p, 3s, 3P, 3D, 4S, 4P, 4D, 4F, 5S, 5P, 5D, 5F, 6S, 6P, 6D, 6F, 7S. Okay, again enough. Okay. First of all, you should be write the electronic configuration of radar. Okay. How do you write the electronic configuration of radar? That is up to ends with 6p6. Okay. 6p6. Then start to write EC is equal to radar. Rn is equal to 86. 1s2. Second one. 2s2. Third one. 2p6, fourth one, 3s2, fifth one, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4 of 14, 5d10, 6p6. Shall we count the numbers? 2 plus 2, 4, 4 plus 6, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 66, 70, 80, 86. Okay, radon is 86. 86 is over. Okay, for that we can derive radon. That is over 86 over. What's the remaining? About the actinum. Actinum is 89. Am I right? Actinum is 89 is equal to 89. Atomic number is 89. I think that it is 86 is over. What's the remaining? 89 minus 86. Only 3 more will remain. Okay. That the start with. We should not fill the F subshell. We start with D 1 electron and S 2 electron. Okay. So we should write the configuration. How will you write the configuration of actinum? Okay. How will you write the configuration is RF, Rn, there is a radon, Rn, 5F, 4F is over, next 5F, there is no electron, 5F 0 electron, after the 5F you should be write which one? 6D, 6D, we can accommodate only 1 electron. After the 6D, there is a next one is 7s 2 electron. S should be completely filled. Okay. Then that means radon goes to 86 electron. 86, 87 plus 2, 89. That is a configuration for actinum. Okay. 89 configuration. Okay, clear. Next about thorium. The atomic number of thorium is 90. How will you write the atomic number of thorium? Atomic number of the symbol of thorium is Th, and then atomic number is 90. How will you write? That is radon Rn. That is 86 over. Okay, 86 over. You should be start with D, not F. Start with where? D. That is 5F 0 6D 2 7s2. That is 86 plus 2 88 plus 2. That is 90. Here, and I told you that there is no 5F1. We cannot fill 5F1. So that is the reason. you should be vacant in F subshell. Okay, there is no phi f1, phi f5 and phi f8. We cannot fill phi f1, phi f5, phi f8. That is why we cannot fill phi f. Okay, phi f, that is always 0. Next, the atomic number is about the 91. Okay, that is Pa. The element Pa is 91. How will you write the electronic configuration? That is Rn. Rn, that is goes to 86 over. Okay, 86 over. And when we are starting with phi f2, not fill phi f1. I told you that phi f1 we cannot fill. Start with where? Phi f2, 61, 61, 7 is 2. Okay, like that you should be fill. We should be fill all the electronic configuration and about which are the having about the completely filled, that is atomic number 102 and 103 are completely filled in F subshell. Okay, atomic number about that 102 and 103. That's the element name is NO. And about that Lawrencea, we are saying LR. Okay, these two elements having completely filled F subshell. Completely filled. That means ask the one-word question. Which are the element having completely filled in F subshell? Can you write the electronic configuration of NO? How will you write the electronic configuration? Rn. That is 86 over. Next about, how will you write? Next about Rn 4f, 5f 40 and about D subshell 6D0, 7s2. Okay, and about Lawrencea, one electron goes to where? 3D1. Here 3D1, that is Rn 5f40, 1s goes to D, 6D1, 7s2. Okay, that is 86 plus 10, 86 plus 10, 96, 96 plus 4, 100, 100 plus 2, 102. Okay, next about here about 103 Lawrencea, how will you write? 86 plus 10, 96, 96 plus 4, 100. Okay, 101, 103. This is the electronic configuration. Here the one-word question. What is the most common state in actinoid? What is the most common state in actinoid? Okay, that's the most common state is +3. Okay. +3 for actinide. Okay. Actinide, the most common state is +3. And about the variable oxidation state. What are the variable oxidation state means? +2, +3, +4, +5, +6 and +7. Okay. These are the variable oxidation state. +2, +3, +4, +2, +5, +6 and +7. When you are seeing the tabular column, we can understand that mostly all elements having +3 oxidation state. Okay, maximum all element. Only few of them, that is only 2 elements having +2 oxidation state, and having some of the elements having +4 oxidation state, and some elements having +5 oxidation state, and few elements having +6 oxidation state, and only 3 elements having +7 oxidation state. Okay, these are the variable oxidation state of Lanthanides. Anyhow, today our very important question is differences between Lanthanides and Actinides. Differences between Lanthanides and Actinides. Here, what are the differences between Lanthanides and Actinides? Okay, here. can we say lanthanides and actinides. Okay, first one, differentiating electron endays in 4 of orbital. Which orbital? 4 of orbital. Differentiating electron endays in 4 of orbital. Differentiating electron endays into the 5 of orbital. Can you write 5 of orbital? Very important question. Especially very important for the 5 mark question. Okay, 5 mark, something maybe ask 3 mark question. Lanthanides, sorry, differences between lanthanides and actinides. Differentiating electron endays in the 4 of electrons, 4 of orbitals. Here, differentiating electron endays in the 5 of orbitals. Okay, here, binding energy of 4 of electrons are higher. Binding energy. Higher. Binding energy is high. Here, binding energy is lower. Okay, binding energy of 4 of orbitals. 4 of orbitals are higher. Binding energy of 4 of orbitals are higher. Here, binding energy of 5 of orbitals are lower. Okay, then less tendency to form complex. Less tendency. Here more tendency, okay. Here having greater tendency to form complex. Okay. What's about the first point? Differentiating electrons endays into the 4 of orbitals. 4 of orbital. Differentiating electron endays in the 5 of orbitals. Binding energy of 4 of orbitals are higher. Binding energy of 5 of orbitals are lower. They show less tendency to form complex. Okay. They show greater tendency to form complex. Here, most of the ions are colorless. Most of the ions are colorless. Okay. Here, ions are colored. Okay. Ions are colored. We should be write any 3 examples. In one or two examples, for example, U3 plus red color, U4 plus green color. Okay, U3 plus red. U4 plus means green. Here, what is about the 4th point? Most of the ions in Lanthanide series, most of the ions are colorless. Here, actinide series, most of the ions are colored. Here, U3 plus, one of an ions, U3 plus is a red in color. And U4 plus is a green color. And also one more having UO2 plus, UO2 please, 2 plus is a yellow color. Okay, UO2. Okay, next about one or 2 points is enough. Okay, they do not form oxocation. They do not form oxocation. Here, they can form oxocation. Here, they can form okay, they can form oxocation. Here, lanthanides, they do not form oxocation. And also about, I told you about the oxidation state. Beside this have +3 oxidation state and also show +2 and +4. Here having +3 oxidation state and also having +5, +6, +7 and etc. also oxidation state. Okay, anyhow, you should be right at least 5 points. What is the first point here? differentiating electron endays in 4f orbital, differentiating electron endays in 5f orbitals. Okay, here about the binding energy of 4f electrons are high, binding energy of 5f electrons is low. There is a less tendency to form complex. That is actinide having a greater tendency to form a complex. Here lanthanides, most of the ions are colorless. Here actinides, most of the ions are colored. For example, examples are very important. The one word question, U3 plus. What is the color of U3 plus? Red color. What is the color of U4 plus? Green. What is the color of UO2? 2 plus is in yellow. Here they do not form oxocation. Oxocation in lanthanides. They can form oxocation, and also we tell about that oxidation state. Besides plus 3 oxidation state is then shows that plus 2 and also plus 4 oxidation state, and about beside plus 3 oxidation state it shows the higher oxidation state, that is plus 4, plus 5, plus 6, plus 7, okay, etc. of the oxidation state. Anyhow, today assignment I am giving that this same question I am giving, that is the differences between lanthanides and actinides. Differences between lanthanides and actinides. Okay. Thank you all of you. Thank you. Have a nice day.